Hello and welcome to the presentation of the Data Intensive Applications and Systems Lab at EPFL. My name is Anastasia Ailamaki. I'm a professor at the School of Computer and Communication Sciences and the lab director. Today, everybody needs to collect and analyze data. You know that already. Just to give you an overview, we have healthcare, government policies, weather prediction, but also sciences and business decisions, all dependent on efficient analysis of data. But data is growing at unprecedented rates. In the last 10 years, only the data has grown more than 50 times, and the curve is predicted to continue at a very aggressive exponential rate. So what can we do about all this data? Well, we can process it into useful information, but how fast can we do that? It turns out not so fast. Our processing technology lags significantly behind the data collection sizes. So in the end, we end up with the ability to process only a little bit of the data that we own, whereas much of the data, which is represented by the growing window here, is left-right only. What can we do? Well, develop technologies to first load only the interesting data, not even store, not even invest into data that's not going to be interesting, and at the same time, be able to explore whatever data that we store efficiently, so boost our algorithms. However, that's not easy because the data comes in a variety of shapes and formats, and our systems do not really agree with that. So the variety, however, doesn't only stay with the data and applications, it also goes to the hardware. We used to have single-threaded hardware that was evolved in the forms of parallelism that it gave to the software, for example, with concurrency that came with multiprocessors and then with multi-socket multi-cores, along with the problems of non-uniform memory access in order to access remote memory in remote sockets or remote machines in a data center. But now today, what's very important is that we can have heterogeneity at the microarchitectural level. We can use for processing devices that used to be only for a specific purpose, for example, graphical processing units. And this heterogeneous compute makes even more complicated the problem of using all the available hardware efficiently, because efficiency, that in this case, doesn't only give us higher performance, it also gives us sustainability, which is very important today. So we have a three-dimensional tug of heterogeneity in database systems in the future: workload, data, and hardware. And I want to start with the data. The data comes in various formats, and in order for any one database system to process data, it needs to be in one certain format. For example, Oracle, DB2, MySQL need data in tables. MongoDB needs data in hierarchies, and so on and so forth. So if you have heterogeneous data, you need to transform it to the format that your software needs in order to use it. Well, that's not a scalable technology outlook. So instead, what we do is that we build a system, we build the infrastructure, which leaves the data in its original format, doesn't load the data or transform it in any way to fit a certain system, and instead we build a data virtualization layer which does two things. First, it makes the data look like the data that the database at hand wants. So if you have, say, for example, a relational database system, and there is a source that has hierarchical data that needs to be used in a query, our data virtualization layer makes the hierarchy look like a table without effectively transforming it to a table before it needs to be used. The other thing that we do is that we adapt our filtering operations to the data that needs to be used by the query. So instead of writing software ahead of time, we create just-in-time code generation infrastructures which allow the just-in-time generation of all the filtering operations of the data that's going to be needed by the query. Therefore, we allow only the data that's needed to be used, and it's used in a customized code-generated way. So this is a self-generated custom database system for every application that adapts itself as the application moves along. Now, The other problem, however, is the veracity of the data. The data scientists today spend 60 to 80% of their time in cleaning and preparing the data. We need a systematic solution that helps reduce this time. Now data scientists take the dirty database, produce a clean version of it by addressing a number of problems that they predict might be an issue, and produce a clean database for use by the analysts. The problem is twofold. One is that there are many kinds of errors, and doing this process for every one error is time-consuming and creates a lot of replicas of the data. So how can we create a data cleaning process that covers all of the possible errors and also detects them in a way that's most relevant to the analysis? Our solution involves an introduction of a common algebra in which one can express any kind of error that might ever happen in the data in a customized way that fits the application at hand. Therefore, the data scientist, instead of cleaning the data, actually starts asking questions, and every question can be annotated with the kind of error that perhaps might distort the results. That using this algebra, we form the question and the cleaning operation at the same time in the same query. This is coupled with a query execution infrastructure that allows us to correct, not just detect, but also correct the error at the same time. So typically, you send the query to the system. The query is executed by only bringing up the data, retrieving the data that's needed for the query, and then the answer is given out. But for our case, for cleaning the data, we develop a relaxed query executor. The relaxed query executor is different than a traditional query executor in that it doesn't only bring the data that's needed for the query, it also brings additional data that help to clean the data that's needed for the query. For example, if there is a value in the data that doesn't agree with the rest of the values and violates a consistency issue, this value might be cleaned by looking at other values that might not be needed in the query but are relevant to that field, by looking at other values, and those values can be used to produce the clean version of the data in real time. So with this unified real-time adaptive data cleaning infrastructure, we can effectively reduce the time that's needed to clean and organize data in an offline way. However, the data, as I said, comes in huge volumes and a lot of times at an unprecedented rate and speed. So for years now, people have been trying, instead of using the entire database to answer their questions, to use an approximate query processing infrastructure. That means that instead of using a classical database to send the queries to and get the answer, people try to find out what will be the workload that's going to use the data, what kind of queries we will execute, and then run a sample on the original database, create a sample database, and instead of sending the queries to the original database, they send the queries to the sample database. If you want to see the relative performance, you can look at the graph on the right-hand side, where we have a query sequence from 0 to 200 queries and the execution time. And if you don't use any sampling, you run the queries on the original database. And so you have a certain amount of time that you need in order to execute every query. If you're going to do sampling, you need to know a little bit the workload, and then you start sampling. You finish sampling, then the query execution time is lower, and so the sampling time is amortized, and at some point you have a sweet spot where your cumulative execution time is lower than if you had not sampled. The problem is, what if you don't know the queries and data a priori? This way you cannot really sample efficiently. You might sample the wrong things or at the wrong rate. So how can you do approximate query processing in an online mode? Well, the way that we can do it is that we first materialize intermediate results, and then we use them for future queries. So while we run the queries on the original data, we start collecting templates and samples in real time. Initially, we don't have any, but as we go along, we start collecting them. And then after a while, this becomes enough for us to be able to run the queries against the sample database. The difference between this sample database and the one we would have executed offline, we would have collected offline, is that this one is very relevant to the workload. So it doesn't matter that we don't know the workload, we actually learn the workload as we go along. So we don't need any pre-processing, we don't need any a priori workload knowledge, and we still can execute faster. The system that we build, called Taster, is actually faster than the offline sampling as well, because it's custom to the queries that are being run, and it's adaptive. The one query after the other is a model that was used up until a few years ago. We had very little concurrency when it came to analytics. The concurrency was mostly for transactional workloads, but today the analytics are involve multiple queries, especially when we're doing online analytical processing. So today we see that systems use much more queries than just one at a time, and this model is giving us a non-scalable execution time. When we go from 10 queries at a time to 1,000 queries at a time, for example, in platforms like Facebook, we cannot keep the execution time scalable, and the system goes slower and slower. So one obvious way to make things faster is to recognize the fact that the queries are typically doing similar things one after the other, and that they're running typically on similar data, especially when they're close in time or run by the same user. Also, flash crowds are very common. For example, if there is a trend in fashion, people are going to be looking at that trend a lot. Or nowadays, with the coronavirus, people are actively looking for information about the spreading of the disease. There are flash crowds everywhere. So a lot of these queries might be executing on the same data and might be able to share data, but also share work on that data, share execution parts, if we could pay attention to the sharing. So sharing can make us execute many fewer queries and drastically reduce the time to execute. However, the problem is that the sharing aware planning is extremely expensive. In this graph, which is conceptual, we see that if we plot the execution time per query volume in a classical query at a time, it will follow the straight line here. Now, if we have the sharing aware planning, which means an optimizer that optimizes many queries at a time and take advantage of sharing, it might do a good job or not, but we will never know because we will spend most of our time optimizing. So planning takes all of the time, that becomes very fast unmanageable. If we could share at the maximum, we would be increasing the execution time in the beginning, but then the execution time will quickly flatten out as we can do a lot more sharing. So instead of first planning and then executing, we execute, much in the spirit of the previous technique that I presented as well for data cleaning and learned approximate query processing. We can execute in a learned way. So we learn the sharing patterns of the workload and we adapt to them. For example, we start executing, and this is the line that's shown here that's called adaptive sharing. We start executing in the beginning, and as we go along, we learn the sharing opportunities from the workload, and we adapt our planning of the execution so that when we execute again, we take advantage of the shared information. This is done with the help of reinforcement learning, and that's why we call it learned multi-query analytics, and has the potential to efficiently execute many queries without increasing the execution time and without expensive planning in the beginning.